Thanks everyone. I just had a friend around staying at home and I said to her, I have to dash out and do this talk. And she said, are you nervous? She's done a bit of acting. And I said, well, I wasn't really into the mention of it, but I could work up a bit of the case of nerves. And she said, well, the thing to do is just to imagine the audience naked. And trust me, it just doesn't work. So, before we wrap up, does anybody have any background in meteorology?
When there's a rainbow, it's raining.
Okay, if we use terms like antitriptic or DALR or lifted condensation level, does anybody know what that means? Thank Christ for that. Okay. Right, so yep, I'm Bryan Tuffnell. Many years ago I got persuaded by Dr. Neil Cherry to do a course in meteorology within a week at university. He was really persuasive. He told me that there were lots of young women starting at Lincoln University. They were all wearing rubber gum boots. And there was no work for meteorologists. So the government was cutting back, so it just sounded perfect, just women and no work. This worked for me for a while, but eventually I sort of figured that actually having a job and some money would be a good thing. But being a student was fantastic. So I did what many of you have done. I went back to university. I got a cadetship in engineering with the post office. If you do an engineering degree, it's nice to have a few fill-in papers that are not too stressful because I'm not doing much work at the moment. I chose astronomy when I won astronomy for one of my courses because most of that was looking at slides of stars going bang. That was fantastic. Just lots and lots of explosions. Just like chemistry without the really good smells. So in that course, one of the things that we learnt was over the lifespan of the sun, which is the same as the Earth and the planets, the sun's temperature has gone up, and it's gone up a lot. And that's reflected if you look at the temperature of Venus and Mars, they've also gone up a lot, hundreds of degrees in the age of the Earth. So this struck me as rather odd because the Earth has always had little oceans. It's always had life. The temperature range of the Earth, it's never changed more than a handful of degrees. It's been really, really, really stable. So I asked the obvious question, how come Earth hasn't changed temperature the same as everything else around it? And the answer to that is that about 3.8 billion years ago, if we take that as being about 150 years ago, carbon dioxide has gone down, oxides of sulfur and nitrogen have gone down, methane went down, oxygen suddenly peaked up, nitrogen did that. All these gases are controlled by life. It's biology that sets the level of those. Photosynthesis is the primary thing. So I spent 4 years looking at how come carbon dioxide has gone down to match the rate that the sun has gone up to give constant temperature. And proving of that takes about 4 years and is completely relevant for us now. But this picture of gases is missing one really important gas. It's a gas whose level changes from place to place, out to out, limit to limit in some cases. And it's incredibly important for us as pilots. It's why it's been so bloody hot here the last few days. It's why we haven't been flying the last few days. Any clues? Water. Bingo. Yeah, H2O. Any idea why? There are a couple of special characteristics about water. One is the amount of water that the atmosphere can hold at any one time depends absolutely on temperature. For every 1 degree of temperature rise, the atmosphere can hold 7% more water.
Can you speak up a bit? Loud back here.
Okay, I'll do my best.
Right.
Okay. That figure is really, really important. The other thing about water is it changes state. It goes from a liquid to gas, to a liquid, to a solid, all in the atmosphere. And as it does so, it does something really important too. If we think of the sun shining on the sea, some water evaporates. When it does, what does it do to the surface temperature of the sea? Any ideas? Right. That's why we sweat when it's hot. Evaporative cooling. It takes energy to change that water from a liquid to a gas. When water evaporates, it takes energy in the form of heat. When that water goes from a gas back to a liquid, it releases that energy. And that's a large reason why it's been so stinking hot lately. And we can look at why. Anybody not familiar with that term? Lapse rate. Okay. Here on the surface of the Earth, we have the weight of air pressing down on us. I know it's imperial, I know most things in imperial, 14.7 pounds of air per square inch. There is more weight at the bottom down here at sea level than there is as we go up. That means there is more pressure down below, which means the temperature tends to be higher down below. So if we draw another graph, sorry about this, there's going to be a few graphs tonight. If we draw a graph of temperature and altitude, as a general rule, temperature decreases with altitude. Sometimes we get a little wonky inversion in that, but that's the trend. Donald, you've asked about tephograms, SQT, SQT diagrams. They are full of these sort of bits of information, what the actual lapse rate is. So as we go up in altitude, the temperature tends to fall. So something that's hard for us to get our head around is that a parcel of air is very bad at mixing with another parcel of air. There's a term that we have for adiabatic. It just means, what that means is if you have a parcel of hot air in an area where there's a lot of cold air, they don't exchange heat very well. Suppose the surface down here is wet and water is evaporating. We've got H2O as a gas in the air. It cools at what's known as a dry adiabatic lapse rate. So that's a rule of thumb. For every 1,000 feet we go higher, the air cools about 3 degrees. Now something happens when it gets cold enough for that water to condense and make clouds. And it's to do with this bit of information here. At a certain temperature, it's too cold for the air to hold its moisture. So it condenses, makes a cloud. You all with me on that? Okay. When it does, that energy that the water has absorbed from evaporating is released. And that's called the latent heat of condensation. So the water gives back its heat into the atmosphere at the level that clouds are formed. So then the lapse rate changes. And it changes to 1.5 degrees Celsius per 1,000 feet. So the next big thing is if we take this parcel of air, we lift it up, we make clouds, suppose we could even make rain, and we dry that air out. And then we drop that parcel of air back down to sea level. It warms at that rate, 3 degrees per 1,000 feet. So we've made that parcel of air warm. Does that make sense? Okay. So if we have, actually we'll do something else. We'll go back. Here's the Earth. Equator, poles. Hotter at the equator than the poles. Okay. In meteorology, nothing's simple. What would happen if there was no convection was the sun would heat the Earth. The Earth would turn the heat that it's received into infrared radiation, fire it back out to space. And the temperature 10 feet above the surface of the Earth would be very cold. The equator would be well below zero. We have greenhouse gases which trap that heat in, and that would make the temperature on Earth about 60 degrees on average, were it not for convection, which lifts some of that heat back out. The poles are the hottest.
Yeah, you got a light switch down there, I can't see what's on the board. Yeah, there's a light switch down
If I change colour, will that help?
Right.
Got a blue.
Oh, I have.
How are we doing?
Try a different colour too.
Sorry?
Any better?
A little bit.
Okay. At the poles, the temperature of the air is increasing. It's expanding. It's become more buoyant. The equator. The air is becoming more buoyant, and it's wanting to rise. What's happening at the poles? You've got cold air is wanting to descend. If all this air is rising, what's happening to the pressure here?
Lower.
Here. Pressure is falling. So what's going to happen to air out here?
So go that way.
Yep. Okay. Air out here is going to be sucked in. So what would happen is we would get a big rotating cell like that. Except for a couple of complications. The main one is Coriolis effect. Why does water go deep and down the sink one way? When you plug it.
The Coriolis effect?
No.
No. Just guessing.
No.
Some magnetism?
Not Coriolis effect, but a surprising number of people think that's why. Dave, can I borrow you? Sure. I'm here, and Dave is the pole. Is the equator. He's going around me this way. Yep. Keep going. Okay, if you stop there, if I'm here and I'm aiming for the equator, and I start walking, you go, stop. I've missed. Does that make sense? I've started from a stationary point, and I've walked towards a moving target, but my target has moved. All this was discovered by a chap called Gustav Coriolis, who was trying to bomb Paris from long distance away. No kidding, no kidding.
Sorry.
He had these massive missiles and he couldn't figure out why they were all veering off to one side. And that's why, if you start here and you aim for that, you're aiming at a moving target. So in the southern hemisphere, you always wind up going to the left because of the direction of rotation over there. If you try and walk in a straight line in any direction in the southern hemisphere, all things being equal, there is an effect which says you're walking towards a moving target and you're going to wind up to the left of it. It doesn't matter which direction you're going in. So the effect of that is, if I'm here trying to go this way, I wind up turning to the left. That surface wind here is turning to the left. That high altitude wind here is also turning to the left. And it breaks up these cells. Sorry, I'll use that other colour. Does that make sense? Okay. We have these two cells here, and a third one clocks itself in as a kind of a gear. This air is descending, this air is descending, this air is rising, this air is rising. So we have three distinct cells. Here there is low pressure, high pressure, low pressure, high pressure. Make sense? Yes. Okay. Where does New Zealand sit? About there. That's pretty idealised. If you look on your phones, if you do a Google of earth.nullschool.net, and if you do that right now, yep.
What's that?
What's that?
What is that?
No.
Yeah. It's more or less like
Okay, if you've got that, if you flip it round so that the South Pole is at the centre, what you should see is Antarctica, and you'll see a whole lot of low pressure cells around it.
that's cool.
If you look really hard, you might be able to identify the other ones. They're not as clear as this guy here.
Turning right.
Okay, so what happens? If you have air rising, you have a whole lot of air rushing in to take its place. You get something called convergence vorticity happening, which is why you get that big spinning effect when you pull the plug out of the sink. If you had 10 of us in a huddle all leaning and pushing, push, there would be a tendency for one of us to get off centre and whammo, we spin. Okay? That's what happens with those swirly bits you see at that junction. The other thing that happens at that junction is you have a collision of cold air coming from the poles with relatively warm air coming down from roughly New Zealand. Whammo, they hit. That's a cold front. You have cold air meeting warm air. Cold air forces its way under. The warm air wants to rise. And to some extent you can see that on that Earth old school thing. So this low pressure area here is a breeding ground for low pressure cells. And low pressure cells there make fronts. They don't at the equator because the air that's coming together is warm. From both sides, it has more or less the same characteristics. This area here at the equator, anyone know what the sailors called it? The sailors had a name for that area at the equator.
Doldrums?
Yep. You know why?
No wind.
No wind. Yep. Not much is happening there, whereas a hell of a lot happens here.
The roaring 40s.
Sorry?
The roaring 40s.
The roaring 40s. Okay, New Zealand sits across the roaring 40s. So, anybody recognise it?
It's Reno.
Yeah, okay. So suppose we have high pressure up to the north of us. Which way does the air go around a high pressure cell? What about if we have a low pressure cell down here? Which way does air go around? Right. where these guys meet. We might have a
Front?
front. Yeah. Okay. The air that's come this way has come from the tropics. It's warm. It's come over a lot of water. A lot of water has evaporated and gone up into that air. It's got to New Zealand. On the west coast here, all this warm, wet air is being asked to rise up over the Alps. As it rises, it cools. As it cools, clouds and rain. What's it been doing on the west coast in the last few days? Yeah. Okay, and it's coming down this side, dry. So let's put some numbers on this. Suppose at sea level on the west coast, the temperature is 20 degrees. This is pretty arbitrary. We said earlier, dry air, air where all the water is still in the air, cools at 3 degrees per 1,000 feet. Suppose, for argument's sake, the cloud forms at 2,000 feet. What's the temperature here? Now, how high are the minarets?
3,100.
What's that in feet? Okay. Suppose 10,000 feet. Suppose it's raining from 2,000 feet to 10,000 feet. What's the temperature here? We said before,
Two degrees.
okay. Now the air is descending at 3 degrees per 1,000 feet. So at sea level here, what's the temperature?
Thirty. 32.
Oh, okay. So we've made a... The air up here starts feeling the Alps a long, long way offshore. The air is piling into the Alps here and building up. So the pressure here is higher. Yep. And correspondingly on this side, the pressure is
Lower.
lower. Right. So, suppose that air is stable. It doesn't want to rise up over the Alps. What can it do instead? Go around. It can go whistling through Cook Strait. When it finds that low pressure side over here, what's going to happen? It can come back as a northeasterly. And I would think, I would be surprised if just about everybody in this room hasn't flown in a northeasterly that is generated by a nor'west. It is really common to have a region on the leeward side of the Alps. Where it's blowing northeast and southwest. And it's northeast on the east coast. That's pretty much the norm. We do get days like the last few days where the northwest touches down and there's no northeast, but that's less common in this situation. So this is the stable situation. The air is reluctant to rise, it would rather go around. And it finds what we call the lee trough here and makes that coastal northeasterly. Really, really, really cool. As pilots, we want to know whether we can safely fly in that northeasterly. And if that northeasterly, if that's starting off as a wet northwest wind, it's blown through Cook Strait, it's come down the east coast, most times it's pretty mellow, it's cool, the guts have come out of it, and it's not too bad. Sometimes it's bumpy. As a vague rule, we fly in this a lot. There's another situation. Suppose it's unstable down near the ground, but the air above is stable. The air up here can come scooting along. It's stable. It's forced to rise over the Alps. But this air has characteristics. It has pressure, it has temperature, it has moisture. It has a natural level of buoyancy that it wants to be at in the atmosphere. If you disturb it, it's stable. It wants to go back to where it was. So it comes hurtling down to where it used to be on the west coast side, to that same altitude, but it also has inertia. It has momentum. So it overshoots and comes a bit lower. And then goes, whoop, I've overcooked it. Scoots back up again. And goes, whoa, I've gone too far the other way. Hang on a minute, I'll get there yet. Look familiar? Okay, standing leg wave. Now, most of the time this is easy to pull off. What are the characteristics? Great, you're nodding your head.
Lenticular.
Yeah, okay.
Chiropractic.
Up here the air is rising. As the air rises, its pressure is reducing. It's cooling. Moisture comes out of it in the form of clouds. And those stacked inner plate clouds are dead giveaway. There's often a cloud like that over the Alps. And really often there are clouds in those parts of the wave. Anybody know what they're all about? Rotor. Okay, the air here is doing this. You can get circulation in here. This is nasty. Those guys have pulled the wings off sailplanes. The US sailplane pilots have a term for them, cumulate granite. Yeah. The wave itself is fantastically smooth. It's brilliant. Any hang glide pilots here have flown in Norway's wave? Warren, have you flown in Norway's wave? Yeah. What height were you getting?
Oh, 10,000 plus, depends if you can stay in.
Yeah. What makes it difficult to stay in?
Speed.
Yeah. Okay. What did the air feel like when you were in it?
If you're in the good sweet spot, it feels very gentle and quiet until it goes out of phase, or if you're in the wrong part, you'll have rough and tumble time of money or either side of it.
Absolutely. If you ride that rising part of the wave here, it's fantastic. It's incredible. It's smooth. It's delicious. It's just way, way, way too fast for a paraglider, and most of the time for a hang glider. The other thing that happens is down here, this is normal the world over, we have something called a boundary layer. The boundary layer is the air that's close to the ground that's affected by the ground. So it picks up moisture, dust, pollutants. It's sticky, there's a lot of drag on the ground. It's sluggish, and wind above it tends to stay above it. This happens, this is quite normal. Now sometimes when we're up on the Port Hills on a nor'west day, we're at the top of that boundary layer. And this happens a lot. You feel puffs of nor'west, and you're thinking, oh yeah, it's probably okay to fly. Gray's shaking his head. Yeah, you may be at the top of the boundary layer. You may be in that lower northeast. What's the danger? Yeah, okay. The wavelength may change and you may find yourself in it. That's one. The other is shear. Everyone familiar with shear? Seen those old guys roll up a cigarette by rubbing it between their hands? You can, if this guy is relatively stationary and you're running air over the top of it, you can get that rolling effect. Some of those rolls can break off and drop. So you can be standing on launch and going, yeah, hey, this is fine. It's only blowing 3 or 4 kilometres an hour. It looks great. I can see there is no wind down the landing paddock. I'm sweet. And you take off, and a minute into the flight, the shear gets you. And doesn't mean you can't have a nice flight, but you must be sure. Okay? There is another situation that you get. Because of where we are in the roaring 40s, sometimes there is just a light dribbling northwest that comes over the Alps towards the foothills. There's no teeth in it. You can be at 6,000, 7,000 feet and think, look, the air is steady. There are no clouds, it's clear blue. I can look down and see that there is no wind down beneath. What can go wrong? I see Simon Harris is on the back. We've done a few flights like this. Mount Harper rings a bell. There's one occasion on Mount Bruce. Mount Binzer. Harper is probably the classic. Mount Oakton. We're in a reasonable northwest. It's soarable if you want to check it. Fraser would be into it. The sky is perfectly clear. Beneath us, we know there's an inversion. We've seen it. We've seen the inversion cloud. We know what the wind is doing down below. We can see water. We can see there is no wind down below. We've just walked up the hill. We know what we've walked through. We know we're taking off and we're descending through it. We know there is no wave. There is nothing but the inversion for the wind to create a shear on, and the inversion is breaking up. We've seen the inversion because of cloud. Fine. Now, I'm not telling anybody to fly in any kind of northwest, but there are situations, particularly inland rather than towards the coast, where you can get away with it, where it's no problem at all, where you can have a nice flight, where the air is smooth. But you need to be sure that what you're flying in isn't the bottom part of a wave system, that it's just that normal roaring 40s wind that you get lightly blowing over the Alps. And then the hazards are what you would expect. It's mechanical turbulence from terrain upwind. But you have to make that call. So that's kind of the northwest. It's hot, it's gusty. It sometimes produces a northeast on the coast. Sometimes there's a boundary layer which keeps it above the ground. It's dry because the water tends to have rained out on it on the western side. We've seen the mechanism which increases the speed. And it's not something to mess around with. So much for the northwest. For the northeast, oh God, that's terrible. That's much better. For the northeast, there are quite a few mechanisms that will produce a northeast in Canterbury. There was a paper that was produced in about 87 which identified 27 mechanisms. So there's no point in trying to cover them all. That lead trough made by the northwest is an obvious one, and we fly in that a lot. Very, very, very often, you get up in the morning, you look on Hull Fully, there's a strong wind showing at Sugarloaf, and there is nothing in Christchurch City. We've all seen that? Yeah. Okay, so that wind is obviously not a sea breeze. Okay. That is a really, really common, in fact I think the figure is about a quarter of the northeasterners in Christchurch occur when there's a high pressure cell to the northeast. So what would the wind be doing here if we looked at the isobars? Yeah. If that's really light, what can be happening here is the upper wind is going that way, the lower wind is just circling underneath it. shift that high around. Yeah. Shift that high around to make a southwest. And that is the perfect situation for a northeasterly in Canterbury. I wonder if I can draw that a bit better. Oh, beautiful. I'm trying to draw it in. So the gradient wind, which is the wind made by that high, is now southwest, and it just doesn't get any better. If we look at what's going on at the surface, it's supposed to be C. The upper wind is southwest. It tends to be stronger at altitude. If this is increasing in altitude, increasing in strength with altitude of low, the local pressure here is quite low. You add a wee bit of sunshine to that, and anything that rises gets pulled round into that stronger flow. And you have that little loop being made. Really common. So what would the signs of a sea breeze be?
Signs of sea breeze.
Yep.
Cold.
Okay.
Salt smell.
Salt smell. Would that make a salt smell?
Moisture.
Okay.
Laminar.
What was that one?
It's laminar.
Laminar. Okay. Would that be laminar? Salt smell, moist? Okay. With a lot of the forms of northeasterly, that guy won't start until there's some heat in the day, nor the sea breeze. If it's blowing northeast up high, if say if there's an actual northeast wind blowing because of the action of a high or a low, it's really common for the boundary layer to be so thick at night that it just doesn't touch the ground. When the day heats up, the boundary layer softens a bit, you get more convection, and that northeast can reach the ground. And it looks a hell of a lot like a sea breeze. At night time, the air cools down, that boundary layer goes all loopy, northeast detaches from the surface, looks just like a sea breeze. And I think for us as pilots, it doesn't really matter. The key thing is if you're flying in the northeast, you try and look at what it's doing at all levels. Sometimes, particularly at a higher site, less so at Taylor's, but somewhere like Allendale, it can be soarable on top, light down below, and very strong higher up. If a boundary layer is weakening, then you would expect the wind speed to increase. So that's really, that and cloud. Those are really the only caveats to the northeast. The wind we can pick up, we can cloud up. Why would it get cloudy?
It's going to see it's getting dry all night.
Okay, and what's it doing to make the cloud form? Okay, what's making the condensation?
Well, temperature difference.
Okay, so the temperature of the parcel of the air must be cooling, dropping. Yep, yep. Cloud, in general, is a sign of rising air. Okay. Sometimes we will get the northwest pushing through. A northeast here. What direction is the sea breeze down here? Southeast. And you can get amazing convergence when that happens. Who's seen it? Big lines of clouds stretching across the plains. Over Lincoln is really common for the northeast and southeast sea breeze to converge. Fantastic. Sailplane pilots use that a lot. Well, they used to back in the days of Woodland. The convergence between northwest and northeast tends to be bloody awful and best avoided. The other one that we get fairly often in Canterbury is a cold front coming up from the south, hitting that northeasterly, and oh boy, spectacular, great lift. One of the things that's happened with climate change is previously, back in the 70s and 80s, in the lead up to Christmas, we used to get a lot of dry fronts coming up from the south. Because they're coming from the south, they're relatively cold, the air is relatively cold. They're displacing relatively warm air, which is lifting. Anybody know what the slope is on a cold front? Okay. Here's the ground. We have a boundary layer. Here's the cold air, warm air. That wedge is almost flat. 50 to 1 to 200 to 1 is the angle. Now, back in the 70s and 80s, we used to get a lot of these October, November, December. Warren, you'd remember these days.
A lot of subtleties.
A lot of subtleties, and they would be dry and they would be massively unstable. We'd wind up with high cloud bases, enough of a wind from the south, so that big cross countries were what we dreamed of. We never did any. But we would have a good time trying. One of the factors with climate change is we're not getting these the way we used to. But in that springtime up to Christmas, that is, if somebody was ever going to fly the length of the South Island in a paraglider, that's what they would do it in, and it would be before Christmas. Another big change with climate change is in the sea breezes. Back in the 70s and 80s again, Allendale, God, I don't know what proportion of the time we would fly Allendale, but over the summer it was a lot, because every afternoon would be a good soarable breeze at Allendale, and now it's all messed up. Northeasterlies that we get tend to be, we're getting fewer sea breezes, more gradient wind northeasterlies that are produced by highs and lows. It's not happening so much. Okay, so the last thing is southerly conditions. If you are hunting down good conditions and you wanted to go inland, it would be from the south, the best you can get. It's certainly not the only condition, but if the wind was coming from the southwest and it was blowing very gently across the Alps from the west side to the east side, that means you're in dry air, you're in rain shadowing. If it's just after the passage of a front, great. You have a tailwind, you have cold air under warm air, so what's the lapse rate likely to be?
Higher than normal.
Okay, should be great. What we're looking for, we talked about dry air lapse rate and saturated lapse rate before, we put numbers on them. When Lorraine's friend Andrew does his talk on RASP, he will almost certainly talk about environmental lapse rate, which is what the air is actually doing and not the theoretical numbers that we presume it to be doing. What we want for thermals is cold air on the ground, warm air above that. Sorry, warm air on the ground, cold air above that, progressively colder air above that, progressively colder air above that. We want a fast lapse rate. That wedge of cold air provides that because that lower 1,000 to 2,000 metres is affected by the boundary layer. That coldness has a chance to disappear. We have the opportunity for the ground to heat up and warm that lower parcel of air. We have the cold air of the cold front sitting above that. And cloud base is probably going to be at about that junction. Give that cold front a chance to come through and go inland. And that's when the big distances will be done. The key to